We're going to look at a different way of examining how things move. We've looked at equations of motion, we've looked at Newton's laws. Now we're going to use two new ideas, some of which you may be familiar with: work and energy. Now, those words have quite general meanings in everyday life. They've got quite specific meanings in physics. Let's start with work. We say in physics that work is something that a force does when it acts upon an object that is moving. We say the force does work on the object. And let's look at an example to see how that might. Here's our car. Here's our car moving along, and we're going to apply a force to that car, let's call it capital F, as the car moves along. And at some later time, the car has moved to this position, and the whole time, this force was acting upon the car. Now, this car may have moved a distance, say from the front of the car there to the front of the car there, of d. That's how far the car moved along. We say the work done on the car by the force is equal to the size of the force multiplied by the change in position of the car, F multiplied by d. That's the work done. And that will have units of joules. That's our unit of energy in the SI system. So the force has done work on the car. Now, another important part of this is that the force has to have at least part of it pointing in the direction of the motion of the object. In this case, the force was pointing in the same direction as the object. There was another force acting upon the car. That would be the weight of the car. It was acting downwards. It also acted all the time as the car moved, but importantly, none of the weight points in the direction of the motion of the car. So in fact, the work done here by gravity turns out to be zero. A force that doesn't point in the direction that the object is moving does no work at all. Now, we can actually use part of our understanding of forces from Newton's laws to think about another kind of work being done, and that is when we were pushing the car, we exerted a force on the car, but by Newton's third law, the car also exerted a force back on us. Now, the car must have exerted a force on us back in the opposite direction with the same size as we pushed on the car, and it must have done that while we were moving along pushing the car. So in fact, we've changed our position here by the same amount, by d, and so now the work done on us will be equal to the force minus F multiplied by the distance. And that is the negative of the work that we did on the car. And so Newton's third law tells us that when one force does work on an object, that object is doing negative work back on the first thing. And that's an important aspect of this. Work comes as positive and negative. I should have mentioned earlier, it's not a scalar. It doesn't point anywhere. So sometimes it's easier to do calculations with work than it is to do calculations using forces and accelerations, because here we don't have to worry about doing our vector calculations. Now we're going to think about energy. Now we've got lots of ideas that we think we know energy coming into our houses, eating some food, getting ourselves lots of energy. There's several kinds of energy we talk about in motion, and an important one is one we call kinetic energy. So kinetic energy here is the energy of motion. That's what the kinetic is telling us. And kinetic energy, we're going to give the symbol capital K, and we're going to say it's equal to a half times the mass times the square of the velocity. That turns out to be the useful combination of mass and velocity. So it's a half mv squared. You might have met that before. How does this relate to work? Well, it relates to work by the fact that the total amount of work that is done on an object by all the forces that are acting on the object equals the change in the kinetic energy. So if a whole lot of forces do positive work on an object, it increases the kinetic energy. If some forces do some negative work on an object, it decreases the kinetic energy. And that's called the work kinetic energy theorem, and it's actually very useful. And it gives us another way to describe motion, again, that doesn't involve forces. Now it involves just work and energy. So let's try an example now where gravity is going to do some work. Let's put our car on an incline, so it's going to change its vertical position. So let's imagine our car is now moving up our incline here at some speed. And it'll have gravity acting downwards, the weight of the car, and at some point later, the car ends up at some higher point. It will still, of course, have its weight acting downwards, and now weight will have done some work because the car has changed its position vertically. It'll have gone up some height here, h. So we can calculate the work done by gravity as simply being the force, which is the weight, mg, multiplied by the change in position, h. And that will in fact be a negative sign out the front because the car is moving upwards and the weight points downwards. So gravity has done work on the car. Now we can actually think about this work in terms of another quantity that we call gravitational potential energy. And we're going to write that as the letter U, and we'll put a little g underneath to remind us to do with gravity, and that we're going to call the quantity mgh. And as you can see, that actually equals the negative of the work done by gravity. So if I move upwards, I increase my gravitational potential energy, and gravity has done negative work on me. If I move downwards, I will have decreased my gravitational potential energy, and gravity will have done positive work on me. So why do I use the term potential energy for this? Well, it turns out that having potential energy gives me the potential to gain some kinetic energy. So let's look at the example of our car again, and we will think about it. It's arrived at the top of this hill here. Maybe it's momentarily stationary, and so it's got perhaps no kinetic energy at the top, but it's got some gravitational potential energy, mgh. Now, the car might move back down the hill. Of course, gravity is doing positive work on it now, and the car will arrive at the bottom here. Now it's got some kinetic energy. Its kinetic energy has increased, but its gravitational potential energy will have decreased. And so it's converted some of its potential to have kinetic energy into actual kinetic energy. And so now we have these three ideas: work, kinetic energy, potential energy. What we'll do in the next topic is see how the conservation of energy principle can allow us to calculate various motion problems.